Hi, everyone. I'm very excited to be speaking here today about the research that I'm doing for my PhD at Stanford University in the Energy Science and Engineering Department. Today, I'll be talking about what I'm calling the University Campus District Energy Consumption Survey, and I'll be diving into the potential energy and CO2 savings from electrification of heating and cooling needs in 30 universities in the US and Canada. Many universities across the US and Canada are interested in electrification options for decarbonization. And today I'll be focused on the potential of heat recovery chillers as a technology to electrify heating and cooling needs on university campuses. Heat recovery chillers as replacements for traditional chillers and boilers are a promising electrification technology because they can provide energy savings, emissions reductions, water consumption reductions, and can reduce the need for traditional infrastructure to meet peak demand. However, heat recovery chillers have often previously been believed to be limited to applications in more moderate climates. One big unknown with heat recovery chillers has been how much savings for all these components are possible based on where they might be installed. So, to answer this question of if there are still significant savings in a multitude of climates and how much savings is possible, I collected heating and cooling data from more than 30 universities, many of which are members of the International District Energy Association. This presentation will be focused on an exploratory analysis that touches on various aspects of electrification with back-of-the-envelope calculations. As you'll see in just a bit, there's still plenty of work that I have planned out for this project, but I'm excited to be sharing these preliminary results with you all today. In the last year, I've reached out to 78 universities in the US and Canada that all have district energy systems. And the results that I'm going to show today are based on the data for the universities that I have already conducted interviews with. This is a work in progress, so I'm still collecting data and conducting interviews. And if you're interested in participating in future research, please scan this QR code and fill out the short survey after my presentation. The US is split up into multiple different climate zones, which represent both temperature and humidity. The numbers for the climate zones go from south to north, with the smaller numbers being in the south and representing hotter climates, and larger numbers being in the north and representing cooler climates. In terms of humidity, that is represented by the letters, which are associated with the climate zones, with A being most of the eastern half of the United States, B representing dry, which is more in the middle of the United States, and C being marine, which is on the west coast. For all of the universities that have provided data for this presentation, there's universities that represent the data for 11 out of the 15 different climate zones. Here you can see each of the different climate zones and how many universities have provided data within that climate zone. Most of these climate zones, as you can see, have at least 2 universities. And again, if you are interested in joining, here's another plug for joining, for scanning this QR code and sharing data for future analyses. Here again, we can see just the breakdown of where those universities that have provided data so far and have gone through the interview process are made up of. And you can see that they are well spread out. For each university that provided data, an interview was conducted, and each of these interviews usually lasted somewhere between 30 and 60 minutes. And each of these interviews were conducted after an initial data share. The interviews were used to collect a combination of both quantitative and qualitative data, which are meant to inform both the research that I will be discussing today as well as future research. There are approximately 20 base questions with follow-up questions based on the responses to those base questions. These questions spanned a large range of topics, including aspects such as participation in demand response programs, if their pipes are buried or in tunnels, what the approximate age of the equipment was, and overall energy system idiosyncrasies. During these interviews, preliminary results were also presented to get feedback on surprises and to ensure that the data was being used and understood correctly. But here we have a couple of examples of interesting metrics that were collected during the interviews. So to participate in the research project, the minimum working data set was 1 year's worth of data. But as you can see here, most universities actually provided much more than that, with the largest time frame being 14 years of data and the average coming out to just under 4 years. 44% of the universities who provided data already have some amount of thermal energy storage. 84% of the universities use some kind of free cooling in one way or another, and almost 30% of the universities already have heat recovery chillers, with many more planning to install them in the near future. And again, all of the universities that provided data do have district energy systems. Now let's talk a little bit about understanding the demand for all the different utilities at these universities across the US and Canada. So here we're looking at the data from a bird's eye view. All of this data that is represented on these graphs show all the data that was provided by the universities for which interviews have already been completed. On the y-axis here, what I have is the total amount of demand for chilled water on the left, hot water in the middle, and steam on the right. And the demand has been normalized by the square meterage that is serviced by each of these utilities, and each dot represents the daily demand for each of those utilities. Here you can see all the different universities on the same graph. Now, the x-axis is the outside air enthalpy, which is a measure of both outside air temperature and humidity. And so here you can see that all the data actually looks pretty similar. And so I've collected data that represents a broad range of universities and climates, but the universities are actually broadly comparable and almost all display thermal demand sensitivity to outside air conditions. And even up to a certain outside air enthalpy, which is about 50, you can see that actually the range of possible demands is not that large, even though these universities vary quite significantly in terms of size, as well as in terms of climate. You can also see that the demand for hot water in general is lower than for steam and chilled water, and this makes sense because there are smaller losses associated with hot water as compared to steam. And there are many fewer universities that are currently using hot water than universities that are using steam because there's a lot of transition that's happening. You may be wondering what this one university is here that seems to be a little different than all the other universities. And this is basically a university that uses a hot water absorption chiller. So basically they are able to use hot water in order to produce cooling during certain periods of the year. And so basically here, what you can see is that even though we have a huge range of universities, the actual demand isn't that variable across different universities. Knowing the outside air conditions, you can basically estimate what your demand might be for chilled water, hot water, or steam within a pretty reasonable range. So now I use these data along with an adaptive regression framework in order to try and estimate what the demand might be based on outside air conditions. So I used a base model, which is illustrated here, that has various different variables that are used within the regression. And so your T can either be your outside air temperature or your outside air enthalpy. H is your humidity. W is your weekend indicator variable, which basically is 1 on weekends and 0 on weekdays. D is the y-intercept, and E is the error term. So basically what I'm able to do with this is use this equation in order to determine what a linear regression might be for the data sets. So here you can see an example of what that might look like with the Stanford data. And basically you can see the R-squared values, which is basically one way to explain how well a regression explains the data that is provided. And here you can see the blue line is the weekday data and the orange line is the weekend data in terms of the regressors and the points. And again, on the x-axis, we have enthalpy, and on the y-axis, we have the total amount of demand. And so we can then use this base model and this regression framework for all the different universities that provided data. So basically, I tried 8 different variable combinations for the regressions, just outside air temperature with relative humidity, etc. And so these 8 are the exhaustive combination with outside air temperature and outside air enthalpy as the base. And basically what we see is that for chilled water, 26 of the universities, the best regression is actually the one that gives the most amount of information. So that includes both relative humidity as well as the weekend indicator. But the base value is the outside air enthalpy. Whereas for both hot water and steam, the best regressor for the largest number of universities is actually outside air temperature, along with relative humidity and weekend indicator. And so this is quite interesting that the chilled water, the outside air enthalpy actually matters much more than the outside air temperature, whereas for heating, for hot water and steam, the outside air temperature is the largest variable. Now let's talk a little bit about the heat recovery potential. So really quickly, I want to introduce the heat recovery chillers. And so this is a diagram for a traditional system, which basically what happens is you have an energy plant, which has traditional boilers and chillers that produce both cold water and hot water. The cold water and hot water get sent out to campus. They get used for heating and cooling, and you have return hot and cold water, which goes back into your energy plant. Basically, what happens then is the return cold water has excess heat because it's been heated up because the cooling has been used. And that excess heat is then exhausted through the cooling towers. And so that basically what that means is that you're wasting heat through the cooling towers. That wasted heat is not being used within the system. However, when you have a heat recovery chiller, they are more efficient because you can actually recycle that waste heat. So again, you have your energy plant with boilers and chillers, you have campus, and then we add a little box here, which represents the heat recovery chiller. So what happens is your return hot water and your return cold water go to a heat recovery chiller. And what happens inside the heat recovery chiller is basically the cold water, which is not as cold as it should be because the cooling has been used, and the return hot water, which is colder than it should be because the heating has been used, get sent into the heat recovery chiller. And basically the heat is extracted from the cold stream and put into the hot stream with a little bit of input from electricity as well as the heat recovery chiller. And basically with that, you're able to produce 1 unit of cooling for every 1.37 units of heating. And that means that basically you are no longer wasting that excess heat from the cold water. You are able to transfer that excess heat into the hot water stream. And with that, you are more efficient. But in order to optimally use the heat recovery chillers, it's often necessary to have thermal energy storage. And so basically for now, for the rest of this presentation, I'm assuming that all the needed storage to optimally use the heat recovery chillers are available. And this 1.37 units of heating for every unit of cooling is a rule of thumb that is commonly used in the field. So now you can use your heat recovery chiller when there's simultaneous heating and cooling happening on your campus. So this is real data for Stanford, with the orange data here representing the heating demands for the campus over the years, and the blue data here representing the cooling demand. And what you can see is that at the same period of time, there's both heating and cooling demand within the campus. Now, if we take advantage of a heat recovery chiller, basically all this purple area that is shown here can be met with the heat recovery chiller instead of traditional heaters and boilers. Now, you may have seen this graph previously because Stanford has presented at IDEA conference in the past. But the interesting bit that was particularly interesting for me is basically the purple exists in all the different campuses that have provided data. And so if the purple exists in all these different campuses, that just means that there is simultaneous heating and cooling occurring on campus. There is a potential for heat recovery chillers. Now, you may have attended some IDEA presentations in the past, like I did from last year, where there were several stories of people saying the heat recovery chillers did not work on my campus. And part of the reason that I believe that they have not been as successful at different campuses possibly can come from the fact that a lot of times these heat recovery chillers were actually being implemented on the building scale instead of at the campus scale. And so here we can see that there is quite a bit of overlap between heating and cooling demands at the campus scale. And basically by going bigger and trying to meet these demands and take advantage of the simultaneous heating and cooling at the campus level, I think there's a much larger opportunity to implement heat recovery chillers than just at the building level. But so what are the impacts of the system of implementing heat recovery chillers? This graph here is just a summary of the table on the previous slide. And so basically what we're seeing here is the percentage cooling met and the percentage heating met of all the different universities, and each of the universities are color-coded by what climate zone they're in. And as a quick reminder, 2 goes from hot to 6 being very cold, and A is moist to B is dry, and C is marine climate. And so what do I mean by the percentage cooling met and the percentage heating met? So again, this is the Stanford data set. So here you can see the percentage cooling would be the area of the purple line for the cooling over the area of the total blue line. And the percentage heating met would again be this area of the purple for the heating divided by the area of the purple plus the orange. So now another way to think about the impact that is associated with installing a heat recovery chiller is looking at a load duration curve. And so a load duration curve is another way to look at load data. And basically what this represents is you take the demand for a utility for the entire year, and you just sort it from largest demand to smallest demand. And so here on the left is your largest demand for an entire year, in this case for Stanford in 2023. And on the right, you have the lowest demand that happened during that year. And so this does not necessarily represent January, and this does not necessarily represent December. They're just sorted by the demand for a single day. And so this is a good way to look at data for a couple of different reasons. The first of which is we can understand what the maximum infrastructure might be that is required and how that might change from year to year. And so basically you need to build out the infrastructure in order to be able to handle the demand day in which the demand was the largest. The problem with this is that you actually end up with underutilized infrastructure. What I mean by this is you built out demand infrastructure in order to meet this demand on this high day, but basically it doesn't get used for the entire rest of the year. In this case, this leftmost point gets used once a year. And basically for any of these points here, basically if you want to build out the infrastructure to this amount of demand, for the whole rest of the year, which basically here represents about, 300 days, this infrastructure does not get used, and so it can be considered underutilized infrastructure. What happens to this low duration curve when you implement a heat recovery chiller? And so here you can see again for Stanford, the red line is with no heat recovery chiller, and the blue line is with heat recovery chiller. And so basically you can see that there are peak power savings, and so basically the amount of demand that must be met with traditional chillers and boilers reduces on any given day. And the actual amount of days that your traditional chillers and boilers are running actually has been reduced quite a bit, where with the heat recovery chiller, you have the heat recovery chiller running most of the year, and the traditional boilers only needed about 200 days out of the year instead of 360. And for any given day, if the boilers are running or the chillers are running, they are producing less than they were without the heat recovery chiller. And so here we can also think about the peak heating and cooling. And so in terms of the percentage of the peak heating and cooling, which are met by traditional chillers and boilers, these can significantly be reduced when you implement a heat recovery chiller. And so here we have the percent reduction in peak heating load and the percent reduction in peak chilled water load. And so this is how much your traditional boilers and chillers are not needing to produce because your heat recovery chiller is actually producing. And so on average, we saw a 26% reduction in peak chilled water consumption and about a 19% reduction in peak heating. Again, these are colored by climate zone, and 2 is hot, and A is humid, B is dry, and C is marine. And then the numbers go from hot to colder. And so here we can see with the back of the envelope calculation what the energy savings from a heat recovery chiller might be for all the different universities. And they are as high as 60% and on average about 36%. And this is assuming back of the envelope calculations with efficiencies for traditional chillers as well as boilers, and then an electric heat recovery chiller. And so you can see that the energy savings are possible across the board with an average of 36%, which is actually quite significant. And now if we translate these to CO2 savings, we can see that the average savings from installing a heat recovery chiller can reduce the CO2 savings on average 32%. And this is assuming average grid intensities for the US. And so again, you can see that there are CO2 savings possible across the board, with some universities seeing quite high CO2 savings and some other universities seeing a little bit less, but still on average quite significant. And so now let's quickly talk about some future work. And so as I mentioned before, using storage can allow you to more optimally use the heat recovery chiller. And so these are some of the universities were able to provide hourly heating and cooling data. And in order for me to have an estimate for what their estimated storage needs might be, I needed hourly data instead of just daily. This is why there are only 9 universities being shown here. But basically here on the top, we can see the heating, and on the bottom, we can see the cooling. And basically what I've done here is estimated the number of hours of storage based on average hourly demand that would be necessary in order to optimally use your heat recovery chiller. These guys, the way they read them is basically this shows the distribution density. And so the wider this shaded area, that means the more percentage of your data is occupied within that range. And so basically you can see that here you have most of your data is actually well below 2 hours of storage, with a couple of different hours within a day that you might need higher amounts of storage. Or most optimally use your heat recovery chiller with actually just about 2 hours of storage. And so basically what you see here is that the maximum amount of hours that you might need for heating never really exceeds 15 hours. But, on average, if you actually get your 5 hours of heating storage, you're actually in pretty good shape. And for cooling here, the numbers are slightly bigger. And so you can see that there is, one university that needs, 25 hours of storage. But for most of them, again, if you're at about 10 hours of storage, you're in pretty good shape. Most optimally use most of your heating and cooling demands. So in terms of ongoing research, there's a couple of different interesting avenues that I'm hoping to take in the future. So one is building level data. For some of the universities, we're able to provide building level data. So trying to understand if the simultaneous heating and cooling is happening in the same building or only across the entire campus. And also trying to understand, what is the building cluster size that is necessary in order to take advantage of simultaneous heating and cooling? Do we need to go all the way to the campus level, or can we use, a smaller grouping of buildings that might actually have the heating and cooling demands at the same time? I'm also interested in doing a deeper dive to understand what the differences between the different universities are within the same climate zone, particularly for climate zones that have more than 3 universities. And also trying to analyze the impact of different data resolutions. And then lastly, I'm very interested in doing a more rigorous statistical analysis of the regressions to estimate impact for future demand. And so that might include things such as instead of just using a linear regression, trying to use nonlinear regressions. With that, I'd like to thank you all for your attention. I'd also like to thank all the different folks that have provided data, which are listed here, as well as many other anonymous contributors. I also would like to really thank the IDEA Campus Energy Conference specifically from last year. I was able to make contacts with all of these people last year, and that's how I got most of the data, was actually by emailing many of you that I'm sure are in the room. And so this project would not have been possible at all without the help of and support from all the people at all these different universities and many other anonymous ones. And so in conclusion, university demands are surprisingly not that different when controlling for outside air conditions. There is some variance, and there's still work to be done in order to understand what causes those variances. But within an order of magnitude, you can definitely estimate what your heating demands and cooling demands might be. The potential for energy and emission savings from implementing heat recovery chillers does exist across the entire United States and Canada, and there's plenty of exciting future work. So with that, thank you all very much. If you want to contribute data, please feel free to fill out the QR code on the right. And hopefully I'll see you at the IDEA conference soon. But if not, you are more than welcome to submit any questions that you might have. My email is right here. Feel free to reach out. I'm happy to collaborate, to answer any questions, and get any feedback that you might have. Thank you very much for taking the time to watch this video.